question of how to calculate conductor size when voltage drop, ambient temperature, and conduit fill are all factors is complex, primarily because the electrical code does not explicitly dictate a specific order of operations. This lack of a prescribed order can indeed lead to considerable variations in the final calculated conductor size. When dealing with conductor sizing, firstly, it's crucial to understand the fundamental parameters that affect the ampacity, which is the current carrying capacity of a conductor. These parameters primarily include the conductor material, its insulation type, the ambient temperature around the conductor, the number of conductors bundled together, and the desired voltage drop in the circuit. Secondly, the conductor material significantly influences its ampacity. Copper and aluminum are the most common conductor materials, and copper generally has a higher ampacity for a given size compared to aluminum, due to its lower resistivity. The insulation type also plays a vital role because different insulation materials have different temperature ratings. For instance, THHN and XHHW are common insulation types with temperature ratings of 90 degrees Celsius, while others like TW have lower ratings such as 60 degrees Celsius. The insulation temperature rating determines the maximum temperature the conductor can withstand without degrading the insulation. Thirdly, ambient temperature is the temperature of the environment surrounding the conductor. Higher ambient temperatures reduce the conductor's ability to dissipate heat, thus lowering its ampacity. The National Electrical Code, or NEC, provides correction factors to adjust the ampacity based on ambient temperatures. For example, if a conductor with a 90 degrees Celsius insulation rating is installed in an ambient temperature higher than 30 degrees Celsius, a correction factor less than 1.0 must be applied to the ampacity. Fourthly, conduit fill refers to the percentage of space occupied by conductors within a conduit. When multiple conductors are installed in the same conduit, they generate heat, and the limited space restricts heat dissipation. This necessitates the application of dirting factors, as specified in NEC Table 310.15. The dirting factors reduce the allowable ampacity of the conductors based on the number of current carrying conductors in the conduit. Fifthly, voltage drop is the decrease in voltage along the length of a conductor. Excessive voltage drop can cause equipment to malfunction, reduce the brightness of lights, and decrease motor torque. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use formulas that take into account the conductor's resistance, the length of the circuit, and the current flowing through the conductor. When sizing conductors, several approaches can be taken, but without a specific code-mandated order, it's essential to consider each factor carefully. Here's a generalized approach, but remember that iterations may be necessary to achieve an optimal solution. One approach is to start with the load requirements. Determine the total current the circuit will need to carry based on the connected load. For example, if you have a 20 amp load, this is your starting point for ampacity. Then consider ambient temperature correction. Check the ambient temperature where the conductors will be installed and apply the appropriate correction factor from NEC Table 310.15. If the ambient temperature is high, this will reduce the allowable ampacity and you'll need a larger conductor. The next consideration is conduit fill dirting. Determine the number of current carrying conductors in the conduit and apply the dirting factors from NEC Table 310.15. This will further reduce the allowable ampacity, potentially requiring an even larger conductor. Calculate the voltage drop. Using the initial conductor size, calculate the voltage drop for the circuit length and load. If the voltage drop exceeds the recommended limits, you'll need to increase the conductor size to reduce the resistance and voltage drop. The final step is to select the appropriate conductor size. Based on the adjusted ampacity requirements after applying temperature correction and conduit fill dirting, choose a conductor size from NEC Table 310.16 that meets or exceeds the required ampacity. Verify that the selected conductor also meets the voltage drop requirements. Another approach is to consider voltage drop first. Start by calculating the minimum conductor size needed to meet the voltage drop requirements. Use the voltage drop formula and the maximum allowable voltage drop to determine the minimum conductor area. Then check ampacity requirements. Verify that the conductor size selected for voltage drop also meets the ampacity requirements after applying temperature correction and conduit fill rating. If the conductor size is not large enough to handle the required ampacity, increase it accordingly. Finally, iterate and optimize. After the initial selection, it may be necessary to iterate through the steps again. For example, if increasing the conductor size to meet ampacity requirements significantly reduces the voltage drop, you might be able to reduce the conductor size slightly while still meeting both ampacity and voltage drop requirements. In real-world scenarios, there are several nuances to consider. For instance, continuous loads, which are loads that operate for 3 hours or more, require the conductor ampacity to be derated to 80%. This means the conductor must be sized to carry at least 125% of the continuous load. Also, harmonic currents, which are non-sinusoidal currents generated by nonlinear loads like electronic devices, can cause additional heating in conductors. In such cases, it may be necessary to further derate the conductor ampacity or use specially designed conductors that are more resistant to harmonic heating. Grounding conductors also play a crucial role in electrical safety. These conductors provide a path for fault current to return to the source, tripping a circuit breaker or fuse and preventing electrical shock. The size of the grounding conductor must be appropriately sized according to NEC Table 250.122, based on the size of the overcurrent protection device. Furthermore, equipment grounding conductors, which connect the metal enclosures of electrical equipment to ground, must also be properly sized to ensure a low impedance path for fault current. Bonding is another important aspect of electrical installations. Bonding involves connecting different metal parts of the electrical system together to create an electrically conductive path. This helps to equalize the voltage potential between different metal parts, reducing the risk of electrical shock. Bonding conductors must be sized according to NEC section 250.102. Additionally, surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning or other transient events. SPD diverts surge current to ground, preventing damage to sensitive electronic equipment. The selection and installation of SPD should comply with NEC Article 285. In industrial settings, motor loads often require special consideration. Motors can draw a large inrush current when starting, which can cause voltage dips and stress in the electrical system. The NEC provides specific rules for sizing conductors and overcurrent protection for motor circuits in Article 430. It's also worth noting that energy efficiency is becoming increasingly important in electrical design. Using larger conductors than required by code can reduce voltage drop and energy losses, leading to lower operating costs. However, this must be balanced against the cost of the larger conductors. In summary, calculating conductor size is a multifaceted process that requires careful consideration of various factors, including load requirements, ambient temperature, conduit fill, voltage drop, and applicable codes and standards. While there is no single prescribed order for considering these factors, a systematic approach that involves iterative calculations and verification is essential to ensure a safe and efficient electrical installation. Always consult the latest edition of the NEC and relevant engineering resources for detailed guidance and specific requirements. Remember that electrical work should only be performed by qualified and licensed electricians to ensure safety and compliance with regulations.